Okay, good day everyone. Um, this is going to be a series of lectures which I will be used for my 2024-2025. If I were to choose to use this again, bear in mind this is based on the batch for 2024-2025. All right, so let us begin with chapter 1, right? So chapter 1, we talk about a bit of mathematics. All right, so we talk about mathematics in the sense that we will be covering a few things, particularly when we apply mathematics into physics. What do we do with it, or at least how we define it? When we talk about physics, we need something physical. That's just in the name. So in the name, we have physical phenomenon, so phenomenon, and then we want to apply maths to it, or mathematics. How do we do that is we introduce this thing called dimensions. Okay, so dimensions is just the physical nature of a quantity. So it's physical, and at the same time we quantify it. Okay, so we begin with that, right? So when we say the dimensions of something, right? So for example, something that is physical, for example, is length, and we want to quantify it, we use probably meters or feet, right? So something physical, when we quantify it, is what we call dimensions. And then we want to make sure that in all our equations we have what we call homogeneity. So let me just change colors. We want to have homogeneity. Okay, so homogeneity simply means that if I have an equation, my left hand side is in the same dimension as my right hand side. Okay, right hand side, HS, sorry. So always bear in mind that in any equation they have to be dimensionally consistent. That's what it means. Okay, so for example, if I were to choose F equals to MA, right, we can have, okay, I have units of kilograms, and then I have units of meters per second, and therefore the unit, so the statement that we'll use is that the unit for force, square brackets represents the units or dimensions, okay, is simply going to be, kg is mass, and then meters is length, and then seconds is time -2. So the dimensions of force is mass, length, over time squared. So that's what homogeneity means. The left hand side must be equal to the right hand side. So that's just to begin our session, and then moving on to units. Oh, sorry, not units. Scalars versus vectors. So scalars versus vectors. As you've learned in SPM, scalar simply means magnitude only, and then vectors means magnitude and direction. Okay, that's what it means. I mean, scalar quantities are quantities with only magnitudes. So for example, temperature. And then vector quantities are quantities or physical quantities that has both magnitude and direction. So for example, velocity. So this is example, okay? For example, velocity. Now, the thing about vectors is that they don't only exist in x direction, they can also exist in y direction and z direction. So in order for you to work with multidimensional vectors, you need to be able to combine vectors and resolve vectors. Resolve simply means breaking them apart. So breaking them apart from a single vector into its x and y components. Okay, so I'm going to just cover how do you combine vectors. Okay, so let's say you have a vector. I'm just going to draw out my x and y axis. So let's call this x. Let's call this y. Now, one of the important features here is that they have to be all, normal to each other. So y and x are normal. What I mean by normal here is that it is 90 degrees from each other. Okay, so let's say I have a vector in x, right? I have a vector in x, and let's give it a name of a. Okay, and then I have another vector in vector b. If I to combine them, what I need to do is going to be using trigonometry. I'll have a product. There we go. I'm going to have a product, or a combination of them. The result of that combination, the combination of them being in both x and y axis. So this is going to be c. So if I were to combine them, a and b, if I were to combine a and b, a plus b equals to c, vector c, I will have to break them down into the components. Okay, so for example, if I look at vector a, I have components of, okay, ax and ay. Okay, and this is simply going to be, let's say we have a length of, I don't know, a equals to 4 units in x, and then b equals to 3 units in y. I'm choosing this because it's easier, because I can immediately calculate that. So in x direction, I have 4 units. In y direction, as you can see, the vector of a does not have any y units, so it should be 0, right? So, and then I have b, which has a x length of 0 and y length of 3. Sorry, y length of 3. If I were to just combine them, what I'll have is I'll have c, which is simply going to be 4 plus 0, which is 4, and then 0 plus 3, which is just 3. Now, if I were to know what's the length of c, I'll just apply Pythagoras' theorem. Now, if I were to just move b, sorry, if I were to just move b to the other side, what I'll have is I'm going to have b here, and then I have a here, a, and then I will have b over here. Now, because they're orthonormal, because they're normal, which means they are 90 degrees, I can immediately apply Pythagoras' theorem. This is going to be 4. This is going to be 3. What I'm going to have is the square root of 4 square plus 3 square, which gives me a length of 5 units. And again, if I were to just find out what's theta, let's just find out theta, right? So theta here, if I take the tangent theta, right? It's simply going to be the opposite, which is b, the length of b, and then over the length of a, right? That's going to be 3 over 4. Okay. And then I'm going to need my calculator for this. My theta is simply going to be 36.87 degrees, approximately. Okay, so this is how you can combine vectors, right? By breaking down or adding the vectors, the vector components of A to B, then to find out what is C. Okay, now if I were to resolve, okay, there we go. Now we have resolving vectors. We can resolve vectors. What that means is simply I have a single vector. Instead of having A and B, I have C. Okay, that's what it means. So if I have Y here, again, they are normal. So X here, I have a single vector, let's call it C, and then I want to resolve it. I want to split them apart into x and y. Okay, I want to resolve it into x and y. No, sorry, it's fine. I want to resolve it into x and y, so let's call this x cx. Okay, so this means that it is the x component of vector c. Okay, and then this dy simply means the y component of vector c. Again, that's what it means. If I were to figure that out, okay, mathematically, let's call that, okay, I can look at it as a triangle again, right, as a triangle, and let's have theta there. Then I can have cx, the length of cx is simply going to be the length of vector c cos theta. Here we use trigonometry, and then I can have the length of cy, right, which is just the length of c sine theta, the opposite. So if I can just move it here, and it's going to be the opposite. Okay, that's what it means. Okay, so it's very important for you to be able to do this because we will be working with two-dimensional cases, okay, especially for mechanics. All right, so we can break this down, and in fact we can rederive our earlier relationship. This one we can rederive this earlier relationship, right, by simply saying, okay, I can have cy over cx, the length of cy over length of cx is going to be c sine theta over c cos theta. Okay, I can cancel those two out. I'm left with sine over cos, which is just tangent theta, which gives us the same relationship over here. Okay, so it's important for you to be able to combine vectors and split them apart. So whenever I say in class, probably okay, you need to resolve this, you immediately think, okay, I'm going to use sine and cos, right? If I were to say, okay, we're going to combine vectors, then you ask, what are the components of the individual individual vectors? Okay, it's particularly important, right? Okay, so that is all, right? We've talked about what dimensions are. We've talked about how we can apply homogeneity, right? We've talked about this symbol. So again, this symbol just refers to dimension of f. That's what it means. And then we've talked about the difference between scalar and vectors, right? And then we've talked about how we can combine and resolve vectors, right? Resolve vectors into its individual components, that is. So what we have is you have to learn how to combine vectors, then you have to learn how to resolve vectors. Okay, all right, that is all from me. Thank you very much